if you guys are uncomfortable with it, I can go over a little more in detail at the end of the recitation. So going back to optimization setting, we can think of optimization as minimizing the loss. If your objective function is maximizing something, then that object minus of that objective function is your loss, basically. It's just a conceptual thing. So usually we want to find the best model that minimizes our loss, given the data x, i's. And then we can introduce the regularization term. If you remember the homework one, the linear regression problems, by introducing the L2 norm, we were trying to avoid the overfitting. And it could be just overfitting, or it could be some kind of constraints we want to impose on the model. And we're going to study about different loss functions and their characteristics and what that means, and different penalty functions in this setting. So if you think about the linear regression problem we saw before.
So going back to the slide about
Sure.
regularization. So in the homework we said that we're adding this, so theoretically we said that if we want to invert the matrix, mathematically it will work if you add the plus lambda times.
Because it's diagonal terms are added, right? Yeah.
Right. So how does the rank property of the negative values relate to overfitting the data?
Not necessarily rank, not necessarily overfitting, but in this setting, if you think about it, you can just in the scalar form, you can just think it about 1 over dividing over 0, then it's gonna go crazy, right? The value is unstable. So you can think it in that form as well, I think. I can talk to you in more detail after recitation. So if you think about the homework one, the linear regression problem, the loss is simply given as the square root of 2 norm of y minus x beta. And the penalty of our problem was 2 norm, but the famous lasso is with 1 norm, which gives sparsity. I can talk more in detail later when I discuss about the penalty functions. And these are just copied over from Wikipedia. So you can have a lot of combinations of these are the loss functions that you can use, and these are the penalty functions. Now, it's good to think about the dual problem, because having loss and penalty can be related to constraint optimization. So if you think about the primal problem, where you minimize f over x, given that there is a constraint that cix function is less than 0, then if you derive a dual function using the Lagrangian multipliers, then you get the following form. Then you can think this as fx as a loss, and this as a penalty function. So yeah, Alex had only constraint with lesser or equal to 0, but more general form has this kind of setting where. So the important thing about, if you guys have questions, I'm gonna talk more in detail at the end. But important stuff about Lagrangian is that, I actually have a slide, I guess, is that Lagrangian function is always a lower bound of the original loss function. Because if you look at here, you're just adding the hix, which is lesser or equal to 0, and then ljx, which is 0, so that if you have those ui's and vj's, so this is important, ui have to be bigger or equal to 0, and then v can be anything because lj is always 0. So adding that function doesn't really change on the proper criteria of x. So that's why it says for feasible x. For feasible x, this Lagrangian function is always lower bounding fx. And then under strong convexity, under strong duality, you have actually, so let me come back to this to the end, because I have backup slides, but yeah. So I mean, basically just remember that Lagrange, because I think you will have to do this in your exams to derive some things, and this is an important concept in solving optimization problem. So because it's a lower bound, you want to push your lower bound as far as you can, and then have an easier form to solve the primal problem, which was just minimizing fx. So
H and L are constraints, right?
yeah.
Inequalities and.
So hix is lesser or equal to 0. So if you do plus times minus, that's just minus. This is always 0. So this whole term is always lesser than fx. So the gist is that sometimes solving the Lagrangian function is much easier than solving a primal problem. So they just change the form. So these are the types of loss functions. This is actually borrowed from the elements of statistical learning. So our model is to try to estimate. We're trying to estimate f, right? And then in learning that, so this is a classification problem. You have label of y is +1 or -1, and then you're trying to. Your prediction rule is, for example, let's say. So if you think about, I know that you guys didn't learn logistic regression, but logistic regression has just let's see, matrix form. Some constant. Then the classification rule is, let's say f, just doing your sin f is your classification rule. So if your sin f is bigger than 0, then you get a plus. Lesser than 0, then you label it as a -1 when there's y equal +1 and -1 labels. So what you can think this is as, so if you look at the first loss function, it's just simply counting how many misclassification you have given your model. So if your y and your estimator sin f has a different sign, which is on the left side, you have a penalty of 1. And then if you have a same sign, you have a 0 penalty. So if we look at the second function, the exponential function actually, that's the light blue one. It's kind of all together, but so what it's doing is trying to penalize it's trying to penalize when it misclassifies, and then when it misclassifies a lot, it's trying to penalize it exponentially, so that as it goes to the left more, so this is the estimator of your y dot f. So if your y dot f is really minus, that means you're really off your classification rule. So you're trying to penalize the model as much as you can. And this is sometimes not very good because there can be anomalies in the data set and so on. So people also use the next one, binomial deviance, which is also called log loss sometimes. So this is this yellow. And it's trying to penalize, it's much smoother than the exponential function. And this is actually the loss function that SVM uses, the log loss. Yeah. Oh, sorry. The logistic regression uses. And yeah, I saw your face. And another thing you have to notice is that on the right side, when it classifies well, it's not it's not trying to get the large margin as much, but when it misclassifies, which means the y dot f has a negative sign, then it's trying to penalize it. What that means is when you classify it right, there's not necessarily there isn't necessarily effort needed to extend your margins for that data set. But when you classify wrong, because you want to have higher classification rate, that you want to change your model a lot. So these are the gist of this. And then the hinge loss is actually, I said it wrong before, but hinge loss is what you use for SVM. And I'll go over later on the comparison of the SVM and the logistic regression. And then we can also look at the regression problem that, I guess I have it here. Yeah. So the error we used on our homeworks are the squared errors. Can everybody see this without problem? On the back, I guess. Yeah. So this again, it's the square loss is trying to, as the power goes up, you're trying to penalize as much as it gets far. But again, this can be a little sensitive to your outliers. If there's a lot of error in the data point you achieved, you observed, then your model will be very dependent on that outlier. So absolute error is absolute loss, which is just the absolute value of the error, is often more preferred mathematically. But then for the reasons that are not discussed in the previous lectures of this course, such as boosting or so if you think about it, differentiability is much better on the square loss. So square loss is also preferred. So what people made is a Hoover loss to have the benefits of both, so that on this delta region where so the green one is a Hoover loss. So in the delta region, you actually have the square error loss. But outside of it, where you might have anomalies, you want to use L1 error for your loss. So looking at it again, you can see it together. And then, as I said, you can compare exponential loss and the square error loss from the classification linear regression, because they're very sensitive to the errors, and the absolute and the binomial deviance, which is smooth. Binomial deviance is really smooth, and the absolute is also much more milder than the squared error. So this is the SVM problem, the primal problem. Oh, go ahead.
Just a question. So in classification, your error is either the signs agree or they don't agree. So when you have a smooth loss function, that's more the regression, right? And then you would interpret the regression if it's positive, or the fitted values. If it's positive, then you predict 1. If it's negative, then you predict -1. But the predictions themselves would not just be positive or negative. They would be smooth.
The function form is also a different concept, but by taking sign of that function, so function can be smooth, if that answers your question, and then you're just taking the sign as a classification rule. So your model both incorporates this function, smooth function or discrete function, and you're taking sign of it. So does that answer your question, or?
I think so.
Yeah. Okay. I mean, this might actually give you more idea. So if you don't have any this soft margin, then you're actually only considering the points which has if you draw wx plus b, then you can draw wx. But by having the constraint that, I guess b minus 1, by having the constraint that this wx plus b minus 1 is bigger than 0, you actually only consider these points, and then as you can see, this is a product with your yi, not this function. So as I said before, SVM is looking at this hinge loss at the end. It's taking the max. Actually, do I have different color? I don't have different color, but what I'm trying to look is this smooth, not smooth, but the hinge loss, essentially. So an interesting part is if you look at the last, the form, it's actually very similar to the logistic regression, which, except the dot product there, because, so it's trying to minimize that loss function, but this is actually using the log, binomial deviance or log loss, people say. And as you can see, the logistic regression has a much smoother loss function. These are the penalty functions that you can consider. Now we cover loss functions. We can cover penalty functions. And as I said, so these are different kinds of norms. If the norm actually goes, if not, the part, let's say it's LP norm, and when the P is less than 1, actually the boundaries of that penalty function actually looks non-convex. So it's actually not proper for our problems, but this is just for your reference. So if we consider the regression problem again, this is the loss Lx given beta. So we said we can add penalty functions to minimize the overfittings and add some sparsity conditions on lasso, or again, avoid overfitting on the ridge regression. So if you actually think about the dual function of that lasso function is since this is loss, minimize this function over beta, given that beta one norm is actually less than some c, let's say. I actually missed one parameter here, lambda, but let's say lambda is 1 here, but you can have any kind of lambda. So what people do is, this is a dual problem, but people actually make it as, is this on camera? The lower? Okay. You can add slack variable. So let's derive the Lagrangian function of this. You can have slack variable alpha, and then what you do is having the same loss function. And since beta 1 norm minus c is less than 0, you can do like this. Now, solving this problem is a little hard because you have to take if you want to maximize it over alpha, you have to take the subgradient of this 1 norm, and then it gets all complicated. But once you know that you get some some solution of this alpha by solving this inner side problem first, then you know that this alpha is just going to be some constant. Then you can just remove this alpha c, and then people just say that solving this problem given this is an equivalent problem and dual problem. So it's a little hard to solve this problem, but then people just say that they are equivalent. And then the reason I brought up this analogy is because I want to give interpretations of the loss of problems and ridge regression problem. So this is, let's say this is the L1 norm of beta that has value less than C. And this is L2 norm of beta having value less than the C. So it's either 1 or 2. Why the loss will give sparsity? Can anybody think? Like looking at the two forms. It's not exactly correct, but intuitively, what you can say is, so this is only when this level set of beta has a tangential derivative of 1. But this is can be any values. And because of this, the corner cases, this can have derivative between -1 to 1. And so what you can think is this, this one point, which has a tangential point 1, is actually moved to this whole plane. And then this, this whole 1/4 area actually moved to this one. So the probability of hitting the corner is actually gets much, much larger, which means that you're trying to force the other components, so given the beta, so if you hit this point, you're forcing beta 1 to get 0. So that means if you hit the corner, that means your other variables are 0, so you're enforcing sparsity in there. Any questions on this? Okay. Yeah, go ahead.
To explain the parts, when you did the dual problem, how did you go from the first expression to the second?
So Lagrangian function is just, so it's,
Where does the max come from?
so this is Lagrangian function here, but dual problem is solving this. So this is maybe a little off this course, but because let's actually go over the whole thing. Oops. Sorry. Let's start from the back this time. Yeah. So your question was, why do you take the max, right?
Yeah.
So I think actually Alex's slide on this is a good. So actually, this is very important concept here. When you have a Lagrangian function. Do you still need this actually? Do I need to write this again or? Okay. Let me see actually. Oh, I thought I had more slides, but that's fine. So if you have let's say this is, so you can draw two pictures. One is on the, so let's say I have loss function. Again, I'll just say beta as my model. And let's follow this notation. So on the primal problem, you have CIX is less than 0, and then when you write the Lagrangian function, your slack, this is called slack variable or Lagrangian multiplier. Your Lagrangian multiplier has to be always bigger than or equal to 0. So what you have is, as I said before, given fixed point x, let's say you have Lx, for fixed point x, your Lx, let's say x naught, your Lx alpha is going to be always under this line if you fix it. But if you also fix this alpha value, if you have alpha naught, then your L x beta is always going to be above whatever formula looks. It doesn't need convexity for this, but this is just simple truth because of this two conditions. Now, there are a lot of proofs and everything going on, but shortly speaking, there are optimal A condition that has this KKT condition where this whole thing is satisfied. So based on what I just said, because you're adding this so this x star alpha star is all called optimal point, and this is called optimality condition. So because when you reach the your Lagrangian function value at the optimal is what we want it to be. So in order to have that at the optimal point, we have to have this value go to 0 because this is the same thing. So that's called vanishing. It's not called that, but Alex said it that way. So vanishing. There's a KKT gap between the primal problem and dual problem, and we don't want that gap at the optimal point of alpha star and x stars. Do you have any problem? Question? Yeah, back to that. So yeah, this line, the saddle point condition, is actually the whole concept of the duality. And then when there actually exists the optimal points, then at that optimal point, the equality can hold at that optimal point. Is that resolved or? It needs like 3 lectures to actually go over.
The max comes from the fact that.
Oh, because it's again because you had this Lx and then at x naught, and you have x naught and alpha. This is function of alpha. So you're trying to push up as much as you can to solve this problem, and then actually at the optimal points, this point actually gets into the, so this is alpha star, and this is function of alpha, whole thing. So that's why you're trying to push up, and then hopefully your dual problem looks, after taking, after taking maximizing alpha, your dual problem of minimization problem looks much easier, hopefully, then you can solve that problem. So that's defined as dual problem.
So you had a min-max before? How did the min-max?
Oh, so when I had like min in front of this, how do I do min-max?
Right. Why did you have the min in front of that?
Isn't that?
So
I'll ask about the max, but then here there's the min before the max.
So our primal objective was trying to solve this problem, right?
Right.
But we know that the Lagrangian function is lower bound of that. And then we want to have dual problem that's as close to the solving this original problem. We still have this minimization, but I'm just saying dual objective is this. So this is a little confusing that I didn't put min here, but.
But didn't the minimization become a maximization in the dual problem?
Right, but that's for the only fixed x naught. But there's a lot of x naughts. So your alpha, after doing this maximization over alpha, the closed form of alpha actually can depend on the x value. So that whole function is depending on the x. It might not actually, if in the simple form, but a lot of cases it does. And then you're trying to minimize it over x. Yeah. Yeah, I mean, I can't. This is all I prepare, but if you guys have more questions on the Lagrangians and the KKT conditions, I can surely go over. Actually, just a second. I thought I had more stuff. But feel free to ask questions in the meanwhile. Do you guys have any questions on the loss and the penalties? Or?
Could you explain the classification slide again, where you had a different
Okay.
possible penalty function?
Sorry. Is it? This is good. So you're talking about this one, right? Yeah.
So here we're just assuming you have plus and minus one as labels, right?
Right.
And then f is what?
So for example, actually, let's go to for this this logistic regression model. So you're given the probably given the data point x and your model is w. So you're actually having this model of linear model wx and then some constant, I guess, w0. And you're defining your probability based on this value here. So that your function, classification rule function is actually whether this is bigger than or equal to 0. I mean, the log function. Oh, actually, confusing. Yeah, this is bigger than or. So your classification is simply if this value gets really big, that means this value gets big, then your probability of being 0 is getting really low. So that, yeah. So this is your model, this thing, and then taking the sign of it. So this is f, and then taking the sign of this f is.
So it's as if we're doing first regression, and then based on the value of the regression, just discretize.
You can. This is not exactly regression, but yeah, that's why it's called logistic regression, but it's not regression. So you have some model, and then you learn this model. So the way you learn it is simply when you have this logistic regression, like for example, on the homework one, we're trying to maximize the likelihood function, right? Given our the regression function. So it's actually very similar to that. So you're trying to, we give a model that says this is our probability given the data set. And then we want to, given observing the data set X and the labels Y, we want to maximize this value. So we do it by gradient descent after getting the log likelihood whole data stream. And then after maximize, so this is the loss function, and by taking derivative on this, you can do the gradient descent and then get the model, specify the model. Once you've specified the models, which means you have the W vector and W0, so that this gives you a classification rule. If this is bigger than 0, you get plus 1, and lesser than 0, minus 1. And then that's, yeah. This is on this scheme of whole thing.
So when y times f equals to 0, it means that actually f is 0, right?
Yes.
So
Yeah.
in this case, you want a loss of 1 for any possible loss function, because you're right at the middle of Like, you don't know who to give more weight to, right?
Right. So, good question actually. Except this the 0-1 loss. It depends on how you define on the 0-1 loss, but except the 0-1 loss, this is all normalized actually to have the same scale. But yes, it goes over 1, the loss. But log of 1 is actually 0. So depending on the
So and for the point 1, 0. So for two of the loss functions, we have a 0 loss for y times f equals to 1.
Yep.
Why would
So that's actually what I was trying to say when I was saying pushing the margin, because because the goal of classification rule is that you want to classify everything right. So SVM is, for example, SVM is trying to maximize the margin between the two labels, the classification rule. But if you think about it, when you when you classify wrong, you want to change your model, but by having it right, you don't necessarily need to change it. So does that answer your question? Or
yeah. I
So-
understand the concept.
so, but for the cases that's close to 0, which is tricky, so you want to penalize a little bit. You want to push the margin, so you want to be safe. But if it's really correct, like for it's really large value, then there's no reason that you want to push margin even more than that, right? So, but for the wrong cases, you want to push it really hard, so it goes up as you get it more wrong to the left. Yeah. I think I'll just stop here. But if you guys have questions about the materials I did today, you can stay. And also, Jin is holding office hours for the homework that's out. So enjoy.